Yeah, so good morning, everyone. Thank you for joining us on this Sunday afternoon. I'm Ashutosh, and I'm here with my colleague and friend Shreyas. And as I wrote in my LinkedIn post a couple of weeks back, we wanted to start an initiative to go over the basics of compilers and the way compiler developers get into this field and how you too can break in. So a few starting points about what you can expect and what it's not about. So this is meant to be a very general overview of the field, things that you can search for. Think of it as that. This presentation will give you an overview of what you have to Google for or what you have to search for to get started. The slides have a lot of links and links to papers, to documentation, to videos that you can go over in your own free time. We'll be sharing the slides with you at the end of the talk, so please don't worry about taking notes or anything like that. If you just listen to what we have to say, that should be enough. You can obviously reach out to us later if you have any questions. So just before starting, I'd like to confirm the screen is visible and I am audible, right?
Yeah, Ashutosh, you're audible and the screen is visible.
Yeah, thank you. Thank you so much. So let's get started. So our agenda today is firstly a gentle overview of the field. We wanted to do this because we could have just started with LLVM, but we felt that it's important for all of the beginners here to know that, why this is important, why compilers are worked upon, where they are used, who works on them, and then Shreyas will give you an introduction to LLVM, a short hands-on. So this hands-on is meant to give you certain commands that you can use to explore the compiler itself, the innards of the compiler, how the compiler breaks down a program. So obviously, you can use the online tools such as Godbolt that are available for this purpose. And we don't require you to have anything installed on your machine just yet. So with that said, let's begin. So basically, what even are compilers? So compilers translate computer code written in one language to another language, and it's not always a higher language to high level language to a low level language. It can also be a high level language to another high level language. One example of this is Babel that converts ES6 to ES5 for all of the web developers over here. If you have ECMA script 6, it can convert it to 5. So that is an example of a transpiler. So that's actually uh, this is actually how a lot of compilers start. Like the very first C++ compiler that was ever written was known as C front, and it was basically a set of macros and other stuff that translated down to C, and then that C was converted to assembly by the C compiler. So, like if you're just getting started out with building compilers or building your own toy language, which is highly recommended by the way, you can always make your compiler output C code, and then you can use that to compile it to machine code. So compilers just don't translate code; they also provide optimizations. So quick note on this: if you would have played old games like I don't know the OG Doom or something, then certain parts of those games and applications at that time were written in assembly. And even today, some niche applications like high frequency trading firms, they employ assembly in some parts of their code, but for most part, it's nearly impossible for a human being to write a large amount of assembly that is more efficient than what the compiler does. So only when you begin to peel back the layers and actually look inside the compiler, right, for what kinds of optimizations it does, basically the compiler can make up for a lot of bad programming. Not all bad programming, but it can optimize away a lot of extraneous things and a lot of unoptimized code. So compilers provide optimizations, and on a day-to-day small basis, you might not notice this difference, but when you're dealing with HPC apps, I don't know, apps like the one used at CERN, or stuff to do weather modeling or quantum simulations or physics simulations, uh, then every every 1% optimization that you do can result in even minutes or hours of runtime difference. So compilers also do optimizations and also error handling. So if our programs just failed without any messages, without anything to be able to debug it, then we'd all be the worse off for it. So compilers also provide error handling. So other than compiling programs, what are compilers used for? So this is an interesting thing because compilers are used in a lot of places where you might not notice. So one example is in domain-specific and device-specific processing. So a domain-specific language is like a programming language that's built only to do one thing. So all of you might have smartphones. So smartphones from, I don't know, Realme, Xiaomi, or any other company that has a Qualcomm processor in it. So the cameras today can do a lot of fancy tricks with photographs, right? There you have bokeh mode, you have monochrome, you have widescreen, you have autofocus, you have a lot of things that the camera can do on its own. And then there are even faster tools for editing it. So for image processing and computational photography, they've created their own language. It's called Halide, and it operates on top of LLVM. And LLVM is something important also that we'll come to. So Halide is an example of a DSL that's used for one specific purpose, to process images on smartphones. Then again, a lot of the tools that are used for that programmers take for granted every day are also built with compiler technologies, which means, yeah, with compiler technologies, like either some part of the tool chain or all of the tool chain. So there are tools such as linters, code formatters, then you have code completion on VS Code. You might have seen IntelliSense. So then there are static analysis tools that can point out things statically. Then there are debuggers. So you have the GNU debugger, then LLDB, all of these debugging tools. So all of these use compiler tech in some way or the other. And that's actually pretty neat because the modern day compiler infrastructure using LLVM is written in such a way that you can use a lot of these components, the front end, the back end, as libraries or as things that as building blocks to build your own tools. And LLVM provides this infrastructure for you to create your own tools to do whatever you want with code transformation and stuff. Then one very major use of optimizing compilers, that is, compilers that are specifically built with optimizations in mind, are high performance computing applications. So there's stuff like weather modeling where you have applications like ECMWF or CESM. So these applications require terabytes of RAM to run and can scale up to 32 cores, 64 cores, and all that because those simulations are really big. So optimizing compilers make a big appearance here. Then there's healthcare. There are projects that are trying to model the entire human heart in a computer so that we can simulate what happens in different medical conditions and how we can treat them. Then there's physical simulation. If you ever sat in a car or airplane, that car or airplane, when it was being designed, it's gone through a lot of CFD simulations and all that, which simulates how the car behaves when it crashes. Obviously, you need to do real world tests, but that can get very expensive very fast. So using high fidelity simulations, you can find out, how the car deforms under pressure, how it performs when there's a lot of air, what are the aerodynamic properties. So for these kind of physics simulations, we have applications like ANSYS, and over here also optimizing compilers are used to build these applications. So one more use, somewhat recent use, is to translate HDL, hardware description languages. So you might have, if you're from an EC background, you might have heard of Verilog or VHDL, or you might have heard of EDA tools that are used to design modern day chips. So compilers have reached here too. There are tools like LLVM CIRCT, which stands for Circuit IR, and compiler tools. So they're used for that too. So what's the status of compilers today? So compilers exist for a lot of languages. Obviously, every compiled language has a compiler, but a lot of compilers exist for C, C++, and Fortran. So C and C++ are expected, but if you're not from a compiler background, Fortran might seem surprising to you. It seemed surprising to me too. But Fortran is still very much around, and there's a lot of optimized libraries and all that are written in Fortran, and there are a lot of applications that are still written in Fortran. So these are the main HPC languages. HPC stands for high performance computing. So these are in open source forms such as Clang slash LLVM and GCC, which is the GNU compiler collection, which you may have used. And there are lots of proprietary compilers from a lot of vendors like Intel compiler, then AMD optimizing compiler, then there's PGI, Cray compiler, ARM. So this is not an exhaustive list. There's a lot of companies. Then in the embedded space, there are a lot of compilers. So again, what's in it for today? There are many new languages that are coming up. So two good examples of them are Rust and Julia. So Rust is again a language that promotes memory safety, and Julia has a lot of features such as multiple dispatch, which is like function overloading, but instead of working at compile time, it works at runtime. So these languages are under active development, and a lot of stuff is being added to them today, and you can contribute to their compilers. Then there are upcoming compilers such as F18, which is a brand new front end for the Fortran language, written with LLVM in mind. This started in 2018, and it is also a work under active development. So a lot of new techniques are also being explored for compilers, such as how to integrate machine learning techniques such as reinforcement learning and others for compiler optimizations. So I don't know too much about this, but it's an interesting space for sure. So some of the,
I think there's a question. So
yeah,
isn't dynamic dispatch the same as runtime polymorphism?
uh, runtime polymorphism, I guess so. Yeah, I mean it's the same as runtime polymorphism anyway, in the way that Julia defines it anyway. So the answer to that is yes. So a few stakeholders in the industry. So compilers are developed by multiple groups of people and in collaboration with multiple things. So the first is we have all our companies, and again, this is not an exhaustive list. There's AMD, Intel, Nvidia, Apple, Qualcomm, ARM. All of these are places that you can work at if you work on compilers. Then there are national labs and scientific institutions such as LANL, BNL. There's CERN. So this is the same CERN that created the World Wide Web, and the same CERN that houses the Large Hadron Collider. They have their own programming language called Root, and they need to analyze massive amounts of terabytes upon terabytes of data. So they also have use for compilers. Then there are specialized labs such as the PACE lab in IIT Madras, and there are other labs in other IITs and other colleges that specialize in compilers. Then there are the open source compilers such as GCC, there's LLVM, there's Oracle's GraalVM infrastructure, which uses Truffle for creating new language frameworks, and there's Qiskit, which is for quantum computing. So before we move on to the next part, there's only a little bit on what do compiler engineers actually work on a day-to-day basis. What kind of things do we work on? So we work on optimizations, which is figuring out ways to extract the maximum performance of a system. Every year, when you see a new processor from Intel or AMD or You see a new GPU from Nvidia. The improved hardware is only one part of the story. Yes, the node shrink, nanometer size of the transistor reduces, and new technologies come up. But then you need to take advantage of those hardware optimizations in software. You need to be able to actually take advantage of those improvements, and those kind of things are done by, in part, by compiler engineers. So stuff like vectorization, inlining loops, inlining functions, unrolling loops, and all that. These kind of optimizations are implemented. So they may be implemented through improvements in the IR, through pragmas. So pragmas are like hints to the compiler. These are usually compiler specific. Then there's implementing new features. So every 2 or 3 years or so, new features are added to C++. So the C++ standards committee, as far as I know it, they usually define, what they plan on adding to new feature to C++ and how it should work. But they don't do the entire implementation themselves. Different compilers keep pace with new features, and sometimes it takes 2 or 3 years after the standard is released for its adoption to be complete. So implementing new features, even in already established languages like C and C++, is still very much a thing. Then there's an underrated thing, which is verification and validation. So a lot of developers take compilers for granted. If there is an error in your code, your first tendency would be to blame yourself instead of blaming the compiler for giving a right output. So compilers have built up that confidence over the years that they are usually right when it comes to analyzing code. So for this, every time something new or something different is added, there needs to be a lot of thorough testing with everything from unit test cases to automated frameworks and code coverage and fuzzing and whatnot. So this includes a lot of scripting, debugging, and cross-checking to make sure that everything is correct. And lastly, research is also a very important part of compiler engineering. Most compiler teams, they also always are on the lookout for new kinds of tools, techniques, and processes. So they're always reading a lot of research papers, writing their own papers, sharing it with the community. And personally, this is a great thing about compilers because the work is always on the bleeding edge, and you get to learn a lot from the community. And even though any company keeps some stuff proprietary, a lot of it does make it into the open source community where everyone can learn and benefit. So one example of this is LLVM Bolt, which is a tool developed by Facebook, now known as Meta. So it's used for optimizing binaries. You can go check that out later. So before I hand it over to Shreyas, so what is LLVM and why is it so important? So we've picked this up as the main to-go framework because, again, you can build a toy programming language such as Cool, or which is Alex Icon's course is there. You can pick up that, or you can build a toy C programming language. But if you are working in a compiler company, or if you are ever picking up compilers very seriously, chances that at some point you will run into LLVM. So what is this and why is it so important? So it was created by Vikram Adwe and Chris Lackner in the year 2000 at University of Illinois Urbana-Champaign, and it originally stood for low-level virtual machine. It doesn't stand for that any longer. The acronym doesn't mean anything now. So its main feature is that it's a modular set of compiler and toolchain technologies that can be used to create a front end. So modular, as in this also sets it apart from when it was created, was that the front end, the back end, the middle end, all of these parts were designed that they could be used separately from each other. So let's say if you had to implement a debugger using LLVM, you didn't have to like code from the ground up. You could reuse some parts of the parser or some parts of the rest of the compiler. So this modularity is one thing that sets it apart. And this modularity is also responsible for uh, uh, its huge support for languages. It has support for C++, Fortran, Rust, Objective-C, C++, Julia, Haskell, Halide, Scala, and many other Golang. So LLVM has a lot of front ends. So this is only possible because of a middle end, and that's known as LLVM IR. So this LLVM IR acts like a layer between you and the computer. It's sort of like a high-level assembly language that can make many of these optimizations and modularity possible. So let's say you have to write a front end for a language. So you have to just worry about lowering to LLVM IR, and LLVM can take care of the optimizations from that point onwards. You don't have to worry too much about the backend. So this makes it very easy for beginners to get into LLVM, and you can learn a lot about the front end without having to learn about the entire backend, which is again a very complicated beast. And one more feature of LLVM is that it has a permissive open source license. So it has a license that you can use LLVM code for commercial use also. So this enables a lot of companies like AMD and Intel both have their compilers that are based upon Clang and LLVM. So Clang is the C and C++ front end for LLVM, and Flang is the Fortran front end. So this permissive license has made a lot of these things possible. And now to tell more about
So I
this thing.
think there's a couple of questions
Yeah,
before
sure.
we switch.
Yeah, sure.
The first question is, could you elaborate a bit on the middle line? The other question, I think is somewhat related. What does it mean by a front end of a programming language and the back end ISA?
Yeah, sure. So those are good questions. So basically, if you let me, I think I'll just pull out some picture from here of stages of compilation uh, so that it can be easier to explain. I should have explained this, so apologies for that. So basically, okay, I hope you can see the image on the right side. So basically what happens is any compiler, right, it breaks down the code. Like you have your, let's say, hello world program. So first you have to break down that code into individual tokens, like the hash include statement, the brackets, and the print statement, and whatever. So you have to break it down into tokens, and then you have to arrange those tokens in a like you have to make sure that those tokens are correct, like that they make sense. So that is like semantic analysis. Then you come to syntax analysis, where you analyze the syntax, and then what happens is first the front end of the compiler is basically converting the code that you have written into a format that can be understood by the computer. Like it generates something known as an abstract syntax tree. So this abstract syntax tree, Shreyas will show you the AST actually. I think once he explains it, you'll be able to understand this more properly. The AST has a representation of your code. And then when you translate that AST into machine code, that part is the backend. So everything that deals with the original programming language, right? The original code, that is the front end of the compiler. And the middle end is what comes between the front end and back end. So instead of translating that AST to machine code directly, you translate it into LLVM IR, and then that LLVM IR can be translated into machine specific code, whether it's for x86 platform. And ISA is just a word for instruction set architecture. So let's say all your Intel and AMD chips are based upon x86, whereas Apple's and ARM's chips are built upon the ARM architecture. So these are CPUs with separate features, and they are arranged in different ways, so they need to be handled differently. So that's what it stands for. The machine code that you need to generate for x86 is different from ARM. So that's the main difference. So I hope that answered those questions. Shreyas, you can take over, I guess.
Sure.
Yeah. Okay. Why we have these parts separated is because again it makes it easier to handle. Like if it was all one block, it would be difficult to handle, but it makes it easier to handle and to actually build out compilers when they are in parts. So I think Shraiysh will carry forward from here.
Yeah, is my screen visible?
Yeah.
All right. So as Ashutosh has covered, what is LLVM and why is it important? Now, let's dive into what LLVM is, how it works, what these front end, middle and back end means, and how you can see it in action. So working on LLVM, you can have two kinds of work on LLVM. First is you use LLVM and its infrastructure, the multitude of things it provides for using it in your external project. The other thing could be to dive into the source code of LLVM and do something with the LLVM project, like implement some new optimizations or add some language features or something. So to use LLVM for compilation, they have their releases like every 6 months, they do a new release and you can download from there and you can directly use the binaries. But if you want to dive into the source code, of course, you have to get it from GitHub and then you have to build it. This is the command line. This is mostly what the command line I use to build. It can be a little daunting to see so many options on this CMake page. And so I've added it here for reference to get people started. And if you don't use these options wisely, your builds can be very slow. So that is also why I've added it here. To use LLVM for compilation. So compiling a hello world program goes according to the figures shown in the presentation. You have a hello world program in C, C++, Go, Rust, or Toy. They have their own front ends, which is like a binary that takes your C source code as input and emits out an intermediate representation, LLVM IR, which is a textual file, and you can see that textual file. Now, this LLVM IR is, like Ashutosh mentioned, it's a high-level assembly language kind of thing, which is machine independent. This LLVM IR then goes into the middle end, which is mainly the LLVM optimizer. What it does is its input is also LLVM IR and output is also LLVM IR. You can eliminate this step, middle end, and you will still be able to run a program because it will go from LLVM IR and that LLVM IR can run on different architectures. And backend is when backend is where you translate LLVM IR into machine-specific instructions, the ISAs. So every machine, like for example, RISC-V has its own instructions. The instructions are not common with x86. They'll be very different. And so what these vendors need to do is they need to only worry about translating from LLVM IR to their architecture, and all the languages will be covered for them. What language communities need to do is they only have to worry about translating from their language to LLVM IR, and all the targets will be covered. So this is a very nice thing about LLVM IR, and it reduces the effort of writing independent compilers for M languages and N targets. So with C, C++, input is a C file and output is LLVM IR file. There are multiple stages in the front end itself. So once you have a C or C++ file, you can see you can just do the pre-processing, which replaces the hash defines, hash includes, and all the pre-processing elements with code. So an example is shown over here. I'm using Godbolt for this, by the way. This is an online compiler runtime environment. So for example, this is your very simple program which prints hello world. And when you pass the -e option to this with Clang 14, Clang is LLVM's C compiler. It gives you this output, which is a huge file. And most of this is nothing but the expansion of hash include stdio.h. And if you'll go at the end, you'll find that here is our main function as it is. So this is the main code, but this is all the expansion, the all hash if conditions and hash if def, all of those get translated in this stage, and there's just one option -e to do that. After this, this pre-processed source code is pre-processed in memory structure is the input to the AST, and the AST phase generates the abstract syntax tree and does semantic analysis on the code. So an example is here. Because the code is very huge when you include something, for this I have chosen not to include anything and have a simple function. And you can dump the AST with the option AST dump. So, okay, I'll explain a little over here. Clang is the C compiler for LLVM. Basically the C front end in the previous slide. If you this part is Clang. The -e option is for preprocessor. The -x Clang option. This means that we are doing something with the front end. And AST dump, as it's evident, it is dumping the AST. The output looks something like this. So for this function, you can see there is a function declaration, and there is parameter variable declaration. There is a compound statement, an if statement, a return statement. Everything is like as it is, and you can do some very interesting analysis, or any static analysis or something on this for specifically for C, and it's used at many places. Now the last phase of front end is IR generation, and an example of that is here. So it's the same example, and this is the option for generating IR. Emit LLVM. -s means in a readable format. LLVM is emit LLVM, and this option is required. So this is required to enable. If this option is not given, there will be no optimizations done. And you might not be able to do them because in the IR itself it's written that you should not, no optimization should be allowed, but that's unrelated. You need not know why this option is required as a beginner. So this is the IR generated, and over here you can see that this the IR generated has instructions like call void. This is not specific to any target. All the languages can dump down to load, store, integer comparison, branch, all these instructions, and these are not at all specific to any target. Target specific instructions will be seen in the backend. All right, so this is the front end. Now the middle end. LLVM IR input is also LLVM IR file, and output is also LLVM IR file, but it's highly optimized. There are many mathematical optimizations that the LLVM community or GCC community has implemented separately. So there are a couple levels of optimizations like O1, O2, O3. There is OFast, there is OZ. There are multiple levels of optimization. But mainly this is a trend that is followed for everything. For all these lines, lower is better. So with O0, you'll have the compilation time will be very small. The binary, the compilation time will be very less. The binary size will be normal, but running time, when the generated binary, will take a lot of time to run because you're not doing any optimization. As you increase the levels, the compilation time keeps on increasing. The binary size more or less stays the same because in O1 and O2 we tend not to increase binary size too much. It doesn't stay exactly the same as shown here, but it more or less stays the same. In O3, it's like we want maximum performance and we do not care about binary size. That is what you get in O3. The compilation time is a little high. The binary size is high, but your performance is a little bit better than O2. And this is the example for that. So on the extreme left, you'll see the LLVM IR. This LLVM IR is same as the LLVM IR for factorial. And if I'm not sure, okay, I can maximize this one. So this is unoptimized code, which is basically recursion, right? Factorial is calling factorial, and it is exactly the same translation. First you do an if statement, then branch based on whatever value you get, you add, you multiply, and you call. Once you, this is in O0, this is in O1, sorry. This is almost no optimization. With O2, you'll be able to see some change in the IR. There is a lot of branching, there is tail recurs, there is vector ph. All these optimizations are trying to do some kind of vectorization, or I mean, if you'll see, recursion has been enabled. Recursion has been eliminated from this of IR now. So this IR should perform better than the original IR. In O3, there is no change with this because maybe no other optimizations are applicable to this. But you'll be able to find other programs for which O3 will have further changes to the IR. This is the middle end. Now in middle end, you can do two kind of things. One is you can run transformations, which means you take LLVM IR and you give LLVM IR. For example, dead code elimination, DC stands for dead code elimination. It can be done in two ways as an option with your LLVM IR file or with the passes option. This is a more elaborate option, a more powerful option. It lets you specify a lot of things. So yeah, and an example of dead code elimination running a pass with an option is just this. So over here you have on the left hand side you have an IR and you are doing addition for two values, but you're not using this anywhere. So basically this is eliminating that unused value. This is a very simple example for that. And there are like hundreds of transformations in LLVM. I mean, not 100 maybe, but like there are many optimizations in transformations in LLVM. There are analysis in LLVM. What an analysis is, it takes LLVM IR as an input and it gives you some information about that LLVM IR. There are this analysis can be anything. It can be as simple as instruction count. It can be as complicated as scalar evolution. So this is how you run it in the current version of LLVM. Earlier they had an analyze option, but I think in the most recent trunk it has been removed. An example of this is here. So this is your source code. It's a very simple code which foo calls bar and that's all based on some if condition. And the scalar, if you do a scalar evolution analysis, it gives you some kind of classifying expressions for at foo. I mean, it's not important right now to understand what scalar evolution is, but what I'm trying to portray from this example is that this is how you do analysis, and this is some information about the analysis that it's dumping out for you. Package is taken, it's taken these many times, and trip multiple is one. All these are analysis specific terminology. Then there is the pass pipeline. Of course, there are when there are so many transformations, it doesn't. You have to have some kind of flow. First, you run this optimization, then you run this, then you run that, and the pass pipeline allows you to do that. For example, pass one, pass two. So for pass one will run first, and pass two will run second. OPT is an LLVM tool. It's used in the middle end. I didn't mention it earlier, but the middle end is LLVM's optimizer is called OPT. And the pass pipeline is much more powerful than just telling run this pass, then run that pass. But the multiple options and how to specify the entire syntax of pass pipeline is in this link in the documentation. So there are many options related to passes and their debugging. For example, how long a pass took, how many times that pass ran, or what is the time trace of that pass. All of that can be seen in opt, help, or help hidden. Now backend, this is machine dependent. Here input is LLVM IR and the output is your assembly basically. But it has two parts, assembler and linker. The assembler generates assembly from basically LLVM IR from a single. So this is using the LLVM assembler for different architectures. This example, the first one is this is ARM assembly from the same IR. The second one is x86 assembly from the same IR. The instructions will be different if you'll see. BGT instruction will not be anywhere here. In x86 and ARM, it's very different. And the third one is, I think, RISC-V. Yeah, RISC-V 32-bit. So the using the LLVM assembler, you can generate assembly for different targets on different machines. So right now, these assemblies are not, of course, they are not, they will run on specific machines, but you can generate them on any machine. The linkers, basically any GNU linker works with LLVM IR generated, LLVM generated assembly because it's assembly ultimately. But LLVM has its custom linker called LLD, which is much faster than other linkers. So, okay. So in backend, there is two links such as machine code analyzer, and example is here. So here you have a C program and its assembly. And this is the analysis over here is showing you different kinds of things like the operations per cycle, instructions per count, all. I mean, this is basically the generated code analysis for generated assembly code. You have tools such as Godbolt have analysis for machine code and information of on code execution. I mean, there are multiple tools, but as I am not personally much experienced with backend, I don't know what these different statistics mean. But there is uh, there's a huge number of tools for us to explore the backend too. There is timeline mode, which tells you how long each in the instruction pipeline in CPU, how long each instruction took in the decode, execute, and wait information. But we are beginners coming to backend stuff, so feel free to explore this on your own. Now, the second part of using and working with LLVM is diving into the source code and doing some changes in LLVM itself. There are a lot of things to choose from. There are over 15 sub-projects in the mono repo itself. There are 2 incubated projects so far as I know, Torch MLIR and Circuit IR. And to get involved and to work on LLVM, you mainly need to answer 2 questions. The first is what you should work on, and the second is how you should work on it. To answer what you should work on, there are a couple of things which I personally know at the moment people can start working on. This is not an exhaustive list because of the size of the LLVM community and the projects it contains. You can implement new and missing language constructs. Over here, the LLVM community documents what constructs are missing and what are partially supported and what are not supported. There is a proper description of every feature, and you can read it and you can try to add support for that. Fixing bugs in existing language constructs. Of course, on GitHub issues, you can find out any bug, and if you think that you'll be able to solve it, you should take it up. There are static analysis tools that you can do on C or C++ programs. So the AST that we saw earlier in the presentation, that AST is very descriptive, and there is an infrastructure to run front-end actions on that AST. For example, find all the struct declarations, and if they have an integer or like many conditions you can have, and you can do some kind of static analysis for this. And this static analysis is basically used by IDEs and safety checkers, data race checkers, and all those kind of things. There are two. This mostly will be independent of LLVM, but you can also propose to add some kind of static analysis to the LLVM monorepo itself. The other thing that you can do is find some new optimizations from research and think about bringing them to the LLVM IR and to LLVM project. There are almost 28,000 results when you search on Google Scholar for LLVM. So there's a lot of material out there. You can improve static analysis tools already inside LLVM. For example, sanitizers like thread sanitizer and memory sanitizer, which checks for data races and memory leaks, etc. You can work on other interesting projects such as MLIR, LLDB, Bolt, LLibc, and there are many sub-projects. The skill set that's required is very similar for all of these sub-projects. So what matters is what looks interesting to you. Open projects are also mentioned at LLVM if you're looking for something more elaborate. They have a page dedicated to open projects, and many GSOC projects go out of this. In MLIR has a separate open project, and it's an LLVM sub-project. So now let's answer how we should do it. After you know what you want to work on out of this list or anything else, after you know what exactly you want to work on, you start discussing how you do it. You can go to discussion forum, discourse, and you can post post a post there saying that I want to work on this particular feature. This is how I plan to do it, and people will be very helpful. People will tell you what are the things that you are not able to foresee right now. They'll tell you this might work, this might not work, and they'll give you good ideas. Discord is also very we have a very elaborate community on Discord where you can ask simple questions and get almost immediate answers. And some examples of such projects that people took are RFCs. RFC stands for request for comments, and if you'll see one of these RFCs, which is about improving plank diagnostics, it has an abstract, summary, motivation, and there's a lot of discussion. There are like 27 replies with this post, and people are helping out the original poster. Of course, feel free to reach out to us and we'll try to help you to work on something. And if we don't know, we'll try to help you to guide to reach someone who knows how to work on something in LLVM. Some pointers when you start working on LLVM. These are very newcomer related pointers, and anybody who gets a little bit experience with LLVM would know these. So for example, the LLVM community uses assertions, a lot of them. So with assertion, the advantage of using assertions is you almost always have to do a release build, which is much faster than doing a debug build. So your compiler development, the development flow becomes much faster. There's the dump function. Almost everything in the entire LLVM subproject has a dump function. So you can see what is happening at any point during the compilation. You can just add a statement to the compiler, to the code, to dump something, and it will dump it, and you'll be able to clearly see what's happening. Arc or Fabricator is the tool that LLVM uses for its reviews, for reviewing the code changes or patches, and it feels daunting, but it has a short and steep learning curve. So don't be scared of it. Just try to spend some time on it, and it will be very easy. Use IntelliSense or CTAGs. This is a personal recommendation because the size of code base is very large. It'll be easier for you if you have IntelliSense or CTAGs or some kind of prediction, some kind of method. Some kind of IntelliSense with you. Add tests for everything. No patch will be accepted without tests. If you don't know where you should add tests for a particular feature that you're working on, you can ask somebody and people will tell you where to add tests in the discussion forums or on Discord. Read the documentation and comments. I personally, when I started compiler development, many times it used to happen that what I'm looking for is probably written in comments or in documentation somewhere, and somebody used to point me to that. So please read the documentation and the comments in code, and also comment your code. Use CMake options efficiently to reduce build times. If your build is taking like 2 or 3 hours, you probably are not using proper CMake options, and you can check with the community what is missing in your CMake options. That's about it. The slides are available here. This is how you can reach us, and these are our calendars. So if you want to book a 1:1 slot for some kind of guidance or something about anything getting started with LLVM, feel free to reach out to us. And if there are any questions, please feel free to ask. Hello.
So I think there's a question in the chat. So why does GCC have multiple IRs like generic Impel RTL, whereas LLVM has just a single LLVM IR? Won't a single IR be faster?
So GCC was developed almost 10 years before LLVM started, and the original motivation of LLVM was to have a set of instructions that all the binaries would run on. For example, right now what we are running on like /a.out, whenever you run a binary, it runs machine instructions. But the original motivation of LLVM was to have binaries in LLVM IR to allow this kind of to solve the problem that GCC had, that it has multiple IRs. You have to write compilers for different IRs for different kind of backend, different kind of stuff. That's the problem that LLVM was trying to solve, and that is why LLVM is a more recent and a better project than GCC.
Yeah, I think it's also the machine IR representation in LLVM for representing or a more abstract representation of the backend. So there are multiple representations in LLVM itself. So there is selection DAG for instruction
Right.
selection. Yeah. So and now there is MLIR project for representing constructs in multiple levels. So I think there's no one IR to rule them all.
Right. One IR gives you portability, but one IR does not give you performance.
Yeah.
So I'll see the other questions from top if there are any. Yeah, the link I'll share it here itself. The link, the slides are on this link. Okay. There are many questions. Just a minute.
Someone asked for the difference between MLIR and LLVM, so I think you can
Okay.
explain that.
Yeah, so MLIR, okay, that might require a lot of time because MLIR in itself is very elaborate and it's so I think the easiest way to tell the difference between MLIR and LLVM is that LLVM has an IR that you can rely on and you can write from like that. There's a fixed IR in LLVM, but MLIR lets you define your own IR and it takes care of, I mean, all you have to do then is define your operations and exactly how they transform into more primitive operations or more lower level operations. It takes care of all the infrastructure, all the binding glue for the different stuff. So MLIR is much more flexible and it gives you scope for more improvements. I'm not sure if I can explain it better. If anybody is, I mean, I'm willing to. If anybody knows a smaller and more appropriate definition, difference. Right, CodeGen is conversion of LLVM IR to assembly. That's correct. Java bytecode is highly different. The Java VM executes bytecode directly in LLVM the intermediate.
I think one good question is how can someone who is stuck in tutorial hell for LLVM get started? So I think this is a good question because LLVM's tutorials itself can be kind of deceptive. The code base moves very fast, so sometimes examples don't work. I think Shreyas can give a good answer for how to get started.
Yeah, I mean, to get started, you have to get out of the tutorial. I mean, you definitely have to take some tutorials in the beginning to understand what you're talking about. But at the end, I would suggest just pick up something, anything, any issue, any feature, any new language construct, or anything from any of the projects, and just ask, how do I work on this in the communities or anyone of me or Ashutosh or anybody like everybody will try to tell you how this is done. It'll be a steep learning curve at the start, but it'll be I mean, you just have to stop watching tutorials at some point. There are many courses which teach you about compiler design, but I would suggest not to go for books focusing on LLVM project because this keeps on changing very frequently. The entire maybe the book came out 2 years back and now many things have changed. So it'll be better if you the courses are also focused mostly on the theoretical aspects of compiler design or the overall structure of LLVM. This course, the Cornell course, this is a very good resource too. Yeah. And how is microarchitecture specific? Maybe for a particular. So there are a couple of tools to work on backend. I personally am not an expert in backend, so I cannot answer this question very nicely. But definitely, there are architecture specific. There are tools to do architecture specific optimizations in backend. So yeah, there is a link in the slides about the slide of this one. So depending on how you want to use LLVM, if you want to work on LLVM, you can follow this link and use CMake to build it. Just clone the GitHub repo and use CMake to build it, and that's all. You can get started. And to use LLVM, just use their binary, set up your paths, and it should be done. I hope that answer your questions, Luck. Okay.
Okay, someone asked it, can contributing in LLVM community get me a job in Nvidia or AMD? So
Uh, I don't. Ashutosh should answer this.
I think the answer is mostly yes. Definitely, like compared to other people who may just have C and C++ experience, having compiler experience directly will definitely give you a leg up in breaking into compilers at least for entry level roles.
Yeah, you also have to clear the programming rounds.
Yeah, that is also there. Nvidia does hacker tests, right? I think.
Well, it depends on the role.
Yeah.
And
Since
there are a
you
lot of candidates.
since you're talking about this, I had a question. So from freshers who haven't worked with compilers before, or who haven't worked with things like compilers before, but they have some exposure in the open source community, what other kind of experience or exposure is expected at these kind of jobs in these companies when freshers apply for these jobs?
Just I think, especially for my team, if somebody knows how LLVM works and can make small changes to code in LLVM and implement features, that should be enough of a skill to be employable. But I
Uh,
cannot say that for sure.
Yeah, I mean, some background stuff that you're generally expected to know is probably some basic understanding of Linux, because a lot of compiler toolchain stuff happens in a Linux environment. So should
Yes.
be comfortable with being able to use the terminal command line. And also some good knowledge of Bash and Python scripting can get you very far in verification, validation level stuff. So yeah, these are some things that you should definitely know. Other than that, if you're generally okay at debugging a code base, then at the end of the day, a compiler is still just a large mass of C++ code, right? So, like that kind of experience may be able to carry over to some extent.
Oh, well, like to be more specific, like so LLVM has LLDB, right? So if someone has an exposure to LLDB and in the process has gotten an understanding of the whole object-oriented code base over there, uh, so would that exposure count as a meaningful one for getting a compiler job? Because it's
That
deep.
depends on how you are able to demonstrate that knowledge, right? Are you able to build some project, like are you able to build a toy language? Are you able to write an optimization pass? You'll just like any other role, like it depends on what you are able to show as proof of work. At least in AMD, we do give all of the candidates a chance to like talk about their personal projects and stuff. So if you have stuff related to compilers, that can be a big help in showing that you take it seriously and you know something about it.
Okay.
Yeah, to add to this, all these companies, AMD, Nvidia, Qualcomm, all of them have different teams working on different aspects of the compiler. So, for example, we work on the core LLVM, the Clang and optimization stuff. But of course, there are teams at these companies who work on LLDB. Who so I mean, it entirely depends on what role you are applying for and what exposure you have.
Okay.
Also, for like I mentioned at the end of the presentation, at the if you want, you can schedule some office hours or working hours with us, and we'll be glad to help you out.
Okay. Thank you, Ashutosh. Thank you. Uh, I'm not able to see your name. Thank
Shrayesh.
you, Teja.
I had one question. So I mean, all the research work uh, is going mainly on these general purpose processors, right? So, how do you comment like specific deep learning accelerators, right? So,
So there is research in almost every phase of the compilation. I mean, I'm assuming you're talking about hardware specific research when you
yeah.
say that. Yeah. Of course, a lot of the research is going on there, but a lot of the research is going on in the optimizations too. And I guess I'm not sure. So there might be a chunk of paper, the research papers in hardware specific research also that use LLVM IR or MLIR to deploy on their hardware. For example, this I think the Sun compiler or something. Recently, I read a paper about this supercomputer where they had implemented a dialect in MLIR for running C code on their supercomputer and achieved real good speeds.
Otherwise, generally it depends on what hardware the company is working with. Like I don't know anything about GPU compilers. It's a whole different world out there. But AMD builds x86 processors, right? So a lot on the x86 platform, whereas ARM works on their own architecture. So some of their stuff may be focused on their own architecture. So it depends upon company to company. No two companies work on the exact same part of LLVM, but yeah, exposure to any part of LLVM generally helps. Like the experience carries over to some extent.
Yeah, but the main thing, the main part is like many of these companies are focusing on the optimization side, right? Like if I'm not wrong, like in the modern
No,
compilers.
I mean,
no,
it depends on what you're working on. Like Shreyas can tell you, in AMD, we're heavily involved in the F18 compiler. That's the new Fortran compiler, and since it's an upcoming compiler, they're working on all parts of the pipeline correctly. Right, Shreyas?
right. So it's important for a company that their compiler supports all the language constructs. What are you going to do with a lot of speed if you're not even able to translate a complete program, right? So, of course, a lot of research is going into doing optimizations properly, but a lot of company effort is gone into, I mean, is spent in getting up to the standards, the language standards, I mean, making sure that it runs smoothly on the target, and of course, bringing all that research from optimizations down to your LLVM compiler.
Okay.
Actually, I had a question. I wanted to ask how can a complete beginner, so like someone who knows a good chunk of C, C++ programming and wants to get involved like in the compilers. So can you give some advice on how to get started for beginners?
Yeah, so like I mentioned in one of the slides, you need to decide what you want to work on and how. The how is basically not very hard to figure out. The what is something that you need to decide. These are the things that I know of that new people can come and pitch in that they want to work on this. But of course, feel free to find out anything new that you want to work on. There are C++ standards, and there are many missing implementations from the newer standards in the LLVM compiler. The older C++ 17, I think, is complete, but 20, 22, for example, 23, all these are not fully implemented, and there is a lot of work that needs to be done over there. And there are like around, I think, 30,000 issues in GitHub and LLVM. So you can pick up any one of those which you feel is not should not be very hard, and you can ask people how should I solve this. So once you figure out what exactly, which sub project and which part of LLVM you want to work on, then just ask people that how to work on this part, and this is my idea, this is how I was planning to do, and can you give some advice, and they'll tell you.
Also, I wanted to ask that, like, apart from C and C++ programming, are there any other prerequisites that you need to have in order to like start contributing to the community in LLVM?
Compiler theory. I mean, of course, you need to
Oh,
understand compiler theory.
okay.
If there's anything else you want to add, Ashutosh or Pratik.
No, nothing else from my side. Anything from Pradeep?
No, I think Shreya's covered it all.
Okay, thank you very much.
I have one follow-up question from the Yuvraj's question. So I have started making some project on this. I started on work on a front end. There's such of terminology like flex, JLX, and kind of thing. So can you elaborate on that? How do we create AST from source code?
Creating AST from source code, this part is like, if you're working outside LLVM project and you are trying to make your own language, this is completely the property of your own LLVM, your own project. And I mean, there is theoretical information on how you can do it. There are courses, there are design principles and everything about ASTs, but you particularly don't need to know anything about LLVM to come down to AST. From AST, you can use LLVM to build LLVM IR. But yeah, that's about it.
And
so,
I'm sorry, I think I'll add to Shreya's answer that Flex is more of Lexer. You need Bison or Yak to generate the AST from there.
Okay, so do we need to learn the front end part to go to the LLVM IR? So where can I get some sample source code for AST so that we can I can directly work on
I think the easiest way to see it in production is just write some short code and then use the flags that we mentioned to see the AST. Then you can change a few lines and see how the AST changes. Obviously, on a large scale, you have access to the LLVM AST reference. It's one giant HTML page with each and every single AST node's description. But I think that to some extent, yes, you'll have to be familiar with the theory because it's like a terminology thing, right? So you'll find it hard to understand the terminology and how all of the parts fit together without any exposure to the theory. So I know that it sounds like we are saying contradictory things, that compilers in theory are very different from how they are implemented, but even then you need the theory to like build a base on top of that.
Actually, I also have another question. Like, I have heard from some of my seniors that in the third year of BTech, they do teach compiler design. So, how relevant is that to like current topic, or is it enough, or we should study something more apart from the compiler design?
I mean, on its own, it serves as a decent intro if it's taught in a good way. But obviously, like as we mentioned, there's a big focus on optimizations and stuff, and most compiler design courses are not focused towards any industrial framework like LLVM. So just like with anything else, just like how colleges have a basic web development course, but you still got to learn all of the web development frameworks and make your own projects. It's just like that. You have to learn on your own and to make use of the frameworks and tools that are available. So yeah, that's pretty much it.
Okay, thank you.
So on this thing about compiler jobs not being celebrated in industry, so I think it's a decent point to bring up. But the thing is, compiler jobs are actually there everywhere. You may not see it. Sure, there might be lesser compiler openings than traditional SDE jobs, but there are also a lot lesser applicants. So it's exposure to a very different type of and unique type of development pipeline. And this is why I'd say that it's a good idea to get started with the open source community and to learn about LLVM on your own, because you have to try it to know if you'll like it. So other than that, it's not like that. There are all major companies such as Microsoft, Google, Nvidia, AMD, Intel, Qualcomm. All of them are working on compilers, and compiler engineers form a very major backbone. Yes, in today's world, there might be lesser excitement about it, but there are a lot of places that hire compiler grads. So yeah.